Hello, coach.
All right,
Coach.
hey everyone. I have my friend Sabaz here. This guy's been inviting me to a pool plunge party. I had no idea what a pool plunge party is,
Come
but
on, dude. Come
apparently you
on.
just hop in a bathtub with a bunch of strangers. Um, but I said let's just do this interview instead. Sabaz,
So
introduce
if I
yourself.
pass this interview, will he come to the punch party?
Yeah, if you get all these questions, I'll come to a plunge party.
Okay, okay. Fuck. Okay, the pressure is high. Okay, I'm Kabaj. I work at AWS. I graduated college in 2023. I study
Nice.
computer science, and I just like to do coding for fun. Like I just build all my apps and just have fun.
Yeah, it looks like you have your own YouTube channel. Like, what got you
Oh,
into starting your own YouTube?
just for man, I'm just trying to have fun. I just coded my own stuff in my free time, so I was like, let me just like live stream it. So that's the only difference. This is usually what I do if I'm not streaming, just like working on my own goofy ideas.
Yeah.
So I thought it would be just experiment, just see what happens.
What kind of stuff are you working on?
Right now I'm working on just like trying to make consumer mobile apps that like integrate like maybe LLMs. So the app that I'm currently working on, it helps you become better at cold approaching people. Like when you're at a bar, like you have the nerves, and you would just want to practice, calm yourself before you approach someone. So started working on that. I shared it with a lot of my guy friends. They've been
Nice.
loving it. I should send it to you as well, James.
I'm down. Send it. Send it.
Oh yeah, I'll send it to you on Discord.
And do you like to use like Windsurf and other AI
Uh,
tools?
I have both Cursor and Windsurf. I think both are same. I personally have had a better experience using Windsurf, but I think both are the
I
same.
see. So
Yeah.
so how do you calm yourself down before you go for a cold approach?
A cold plunge?
Cold
Uh,
approach, you said. That's what
oh,
you
cold
said.
approach. I
That's what your app
honestly,
does, right?
yeah, I feel like it's more of like a placebo effect. Like once you do a lot, like it's the same as doing a lot of mock interviews. Like I've done a lot of mock interviews, and so now it just feels like second nature to like just do like a lead code question on the spot
Yeah.
and be perfectly fine if it doesn't go my way. So yeah, like I used to like use this website to do a lot of like mock interviews, and like that helped a lot. I did this during college.
I see.
Um,
No, I said cold approach. You said you have an app for cold approaching.
Cold approaching, yes. It's not published yet, but I will publish it.
Yeah, but what
Yes.
is your strategy? How do you do the cold approach and
Oh,
calm your nerves
you
down?
honestly okay. So you can practice on the app. Like practice a different scenario, like because usually you approach someone and they just like outright reject you. So like, how do you deal with that? You
How
you
do you deal with
you,
it?
you just you're just like, hey, all right, cool, man. Have a nice day, and just walk away. On to the next one.
Okay. How do you calm your nerves before you go approach and actually go
Oh,
approach?
I see. Honestly, calm your nerves. You just gotta like if you have nerves, you just gotta thug it out. Like it doesn't matter. You just gotta walk up, be confident. Dressed up nice, smelling good,
Nice.
great body language. Just introduce yourself. Hey, I'm Shabaj. What's your name? And you just have to see how the other person responds. If their body language is receptive, you can talk to them. But if they're very like reserved, then just say hi and move on.
I
That's
see.
what I've learned.
This is exactly why you work at Amazon, man.
It's exactly how like
What
explain.
school did you go to? Like, and do you? Yeah, go ahead.
I went to it's a state school in California. It's called Cal Poly.
Nice.
Uh, yeah, that's where I went.
Cool.
It's,
All right. How many leak code questions you've done, and like, what's your level? I need to figure out.
I my lead code is Yummy Shooter. I'm Yummy Shooter.
Or
I
how
I
many?
I've done like about 300, and I can do like mediums, and most of the mediums in like 15 to 20 minutes.
I see. Most mediums in 15 to 20.
Yeah.
Okay.
Like I've done like all the Blind 75 list, all the premium Explorer cards, like when I used to grind in college for like
I see. I see.
yeah. So I would say I'm definitely like I can like I've solved 22 hards, but yeah, like let's just have fun, dude.
Yeah,
Who
yeah.
cares?
Let's get
Give me the
this.
most insane hard question. Let's just
Now we'll warm it up. We'll warm it up.
we're gonna warm up. Okay. Okay, let's do it. Let's do it.
You like to use Python?
Yes, Python. I actually
Okay.
don't use Python for anything, but for interviews, yeah,
I
like
see.
it's a lot easier. Okay. What are we gonna
Okay,
get?
try to do two questions in the span of 40 minutes,
All right,
20
let's go.
minutes each. Let's hop in this right now.
Yeah.
So you're given the root of a binary tree. Imagine you're standing on the right side of it. Return the values of the nodes you can see, order
Hmm.
from top to bottom.
Okay, can you give me an example of like yeah, 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 like how the tree? So given the root, imagine yourself standing on the right side of it. Return the values of the nodes you can see ordered from top to bottom.
Okay, I'll show you one
Okay,
example.
yeah, yeah, yeah.
Go hit the drawing board.
Oh, you're on the drawing board. Oh, I see.
Yeah.
Yeah, yeah, I see the drawing board.
2 5 right here.
Yeah, yeah, yeah. 2 1 2 5. Yep.
Okay. If I want to see the right side of the view, what does that even mean? What do you
I
think?
think I think it should be 1 3 4.
Exactly.
Yeah, 1 3 4.
What about if I have like a 6 here?
Yeah, yeah. 1 1 3 4 6.
What if I have like a
One
0
three four.
here?
Yeah, 1 3 4
What
6.
about if I have a 2 here?
1 3 4 6 2.
All right. Okay.
Yeah, yeah, yeah. Okay. So let's like write it down in the code comments so we can use this example. Uh, or unless okay, fine. So we have two, we have three, we have five. Wait, oops. Five, and then we have four. Then five had okay. 0 6, and then two. Okay, or let's just say seven. So one, so two. Okay, I just want to make sure I have the tree out in the comments. I have it look correct. Okay, so in this case, if we want to see the right side of this tree, it should be 1 3 4 6 7. So that looks fine. And if it's like let's just think of like what are some like normal like if the tree is just a node with one, the answer should just be one, correct?
Yeah.
Oh yeah, 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 cool. So I think the first thing that comes to my mind, what we can do is we can do traversal of this tree. So we can traverse all the nodes in this tree. So traverse all the nodes in the tree, and we can either pick BFS. I think both would work. And each time we traverse, we just keep track of the level that we saw that node at. So keep track of level the node was discovered, and then so it's more like a level order list. So let's just say on level zero we saw one. On level two, on level zero, on level one we saw 2 3. On level two we saw 5 4. On level three we saw 0 6. In level four we saw 7. So it looks like okay. So I think in this case we should do DFS, traverse all the nodes in the tree using DFS, where we visit the left, or I mean, oh wait, let me close the drawing board.
Yeah.
Wait, how did okay done? Uh, where we visit the left subtree first, right second, um, and then keep track of level the node was discovered, and then once we're done with the traversal, return the last element from each level. And I think this approach would take time of O of n and time complexity of linear time complexity and linear space. So that's the first solution I can think of. What do you think of this?
I think that works. Linear
Mm-hmm.
time, linear space. Yeah. Go ahead and code it up.
Okay, cool. Okay, let's just see your right side view, and like I'll just make like a class node just so let's just say it has like self left something, self dot right not something, and it'll have like we can implement this class later, but just to have it as a reference, like it'll have a left right, and we'll probably be past the root node. If root node none, just return none, and then we here do DFS. We can pass in. So we'll need this helper method to help us do DFS. If node none, return none. And let's just say level map. Let's set this to something. Let's also pass in the level map in the DFS function.
Sure.
Well, we'll also need current level to keep track of the current level that we're at. And then we'll call this our helper function. We'll pass in our root node. We'll pass it our level map, and we'll pass it our current level, which should be 0. So once we're here, we will add our current node to the level map at that specific level. So this should be level map, and so it will also, it also has some value which set to 0, and we only need to return the values of the nodes. Okay, so we only need to return the value of the node. So level map at current level should be level map dot get the current level. If current level, if it doesn't exist, return an empty list, and then we can just add node.val. So level map, we get the current level. Then from the level map, we get the current level. If nothing exists, we return an empty list, and then we append that. And then what we then have to do is DFS node.left level map current level +1, then call node OK. Wait, level map current level +1. Then once we're here, once we're done with this DFS, once we come out, let's just say like right view can be, this is our answer, and then at the end we will return our right view. So now here we just need to populate that right view. So our min level is 0, our max level would be we can just do max of level map dot keys. So we can just like get the max key from our map. Then we can just do for IDX in range min level max level +1 right view dot append level map. Let's use the level. That's a better variable. Level map at level, the last element. So we start from the 0th level, and we find the max level, or the max, the max level, and then we our level map. We look up that specific level and grab the last element.
Okay.
Yeah. Let's do a dry run. What do you think?
Yeah.
What do you think?
Dry run it.
Oh yeah, cool. Let's do that. Okay. I'll copy paste this here. We'll also make our level map and our right view. Okay, cool. So let's okay. Looks fine. Okay, so we have our root node here on line 52. We have our level map, which right now is empty, and our root node is here, and our level is currently, we're at the 0th level. So we're going to call DFS here. We're going to call DFS on the root node. We're going to pass that root node. We're going to pass that node here. So right now, our node is going to be 1, which is the root node. Our level is going to be 0. Our level node is going to be empty. Our current level is going to be 0. And then what we're now going to do is level map. So let's also store our level map. So we're going to do level map dot get 0. There's nothing in the 0th level, so we'll return an empty list plus the value of that node and set that level in the map. So
Yeah.
Uh, okay. So 0, and here we'll set 1, and then we will then do DFS on the left subtree, which should be 2. So this would be 2. Our level map is here, and then our level would just become 1. So we'll come here. Um, we'll come here. Our node is not none, so we will then see our current level, which is 1, and we will set its
Okay.
value. Yeah, so this will be 2. So now we will now similarly now since we're still at 2, we will then look at it doesn't have a left child, so for the 2 we'll go to its right child, which would be number 5. Uh, level map, we have that, and our current level will be 2. So once we come here, we see we have nothing for 2, and we'll set that. We'll set level 2 and set 5. And then now we're at node 5. We will then go to its left child, so which would be 0, level map, then level would be 3,
Okay.
and then we would set 0. So we would populate this list, and similarly, we would explore its left. It only has a left child called 7. So then we will come back up. We'll come back to 5. And where did we see 5? So 5 was 5 had 0 on level 3. So we saw 5 at level 2. We explored its left subtree. Now we will explore its right subtree, which is 6. So 6. Once you come back up the recursive stack, it'll be 6. At that point, the level would be 3, and the level would be 3. And once we come here, we see that the level is 3. We already have set it to something, and
Okay.
we'll just append 6. And so this would be we're now done with the whole entire left subtree, starting from
Yeah.
root 1.
I see. Okay. Let's move on to the next question.
All right.
Good job. Um. Yeah. Chug that water.
It's Diet Coke, actually, bro. It
Why
helps.
diet?
Um, well, it helps with restricting hunger. Or it's like the same effect as caffeine.
I see.
Ooh, okay. You're given a network of nodes labeled from 1 to n. You're also given times, a list of child times as directed. Source node signal to travel from the source to target. We will send a signal from a given node k. Return the minimum time it takes for all, if it's possible, for all the nodes to receive the signal. If it is impossible, return 1. Okay, let me read it through. You're given a network of nodes labeled from 1 to n. You're also given times, a list of travel times as directed edges. Okay, where UI is the source node, VI is the target node, and WI is the time it takes for a signal to travel from source to target. We
Got
will send a signal from a given node K. Return the minimum time it takes for all the nodes to receive the signal.
Yep.
Okay, I think I understand. I understand.
You can
Like you
walk
have,
through it. Whiteboard it for me. Like whiteboard me an
yeah. So
example.
okay, yeah, yeah. So I think so let's just use a simple. I'll use maybe 5. Let's use 5. I think I have like an idea. So let's just say this is let's just make this so it's a directed graph. So let's just use arrows, and let's just oh let's just make an edge from every node to every other node.
Sure.
Uh, and then each node has a weight. Uh, each node has a weight. So let's just say like this is node, so it takes like 5 seconds to travel.
Here, let's start with this very basic case. I'll
Okay,
remove
okay.
it. Right.
Sure,
Let's
sure.
put everything as 1.
Oh, okay, 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 okay.
Okay, this is the source. What should be the answer here?
And no, no, which is the final node? Oh no, we have to make sure that we have to make sure that if the signal starts from S, how much time will it take for all the nodes to get the signal, right?
Yep.
So in this case, um, this node will take 1 second, this node will take 1 second, and this node will take 2 seconds. So it should be 1 plus 2 plus 1, and this one, oh, this node will also take 1 second. So 1 plus 1 plus 1, 3 plus 2, 5. I think it should be 5, right?
Wait, let me draft up this solution to two. I think it should only be two because what we're returning is the amount of time it takes for all the nodes to receive the value.
Oh yeah, yeah, yeah. Oh, I understand. I get it now. Because in 2 seconds, all the other nodes would have received the signal too, right?
Yeah.
Oh, I get it now. So it looks like the answer would be like the max, like which. So the answer should be the time it takes to the time it takes to get to the node that receives the signal at the very end. Like, does that make sense?
Yeah.
Oh, I see. I understand that. So it looks like. Hmm, 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 hmm. Okay, let's try another example, just so I can make sure I understand this correctly. Let's um, let's try different values. Let's try different values, and I'll try to do this quickly. And for let's just say this is it takes 5 to travel down here. It takes 2 to travel down here, uh, and it takes 4 to travel down here, and it takes 3. Just random values. 1, 3. So it looks like on to me it looks like the shortest path, or not like a shortest path problem, but we're using like a directed, or we're using a graph that has like weighted edges.
Yeah.
Yeah, that's so. Okay, I see. So I think what we need to do is like from the source node, we need to. Oh, okay. So from the source node, if this is the source node, what we need to do is find the shortest path to this, like what's the shortest path to this node right now, like it looks like, so if you go down 5 4, we don't have a graph that goes this way, so signal is only coming down, so we can take 3 2, it takes 5 seconds, but then to get to this graph we can also take this path, and that looks to be the shortest one for this node, so here the answer should be 2. To get down to this node, we
Are you
only
saying
have.
these are weighted one, or what?
Oh no, no, these were weighted. Whatever I had before. Did you not?
I don't
Let's
see
just.
that.
Oh wait. You're not seeing them?
Wait, let me refresh. Let me refresh.
Okay, okay, no problem, no problem.
Okay, two
Two.
and
Let's
two. Okay.
just 2 4. Um,
Okay.
and and
So
then
how much time should it take to get to two?
oh, so no. How much time should it take? Wait. How are you asking? How much time should it take to get to this node?
Yeah.
2 seconds, I think.
Mm-hmm.
Like that would be the shortest path, because right now there are two paths to get to that node. Either you go from the center, or you like take the direct route. But if you go from the center, it'll take you 6 seconds. But if you go from the source, it'll take you 2 seconds. So the shortest path to that node is 2 seconds.
Okay.
So this should be 2. So that's 2. Then to get to this node, let's just say there's also a path from there are two paths. So you can go directly from the source, or you can go from the middle. and let's do this one differently. Let's just say from the middle it's faster. So you take 2 seconds to get to the middle, and then 1 second to get to that. So it'll be like 3 seconds total. So the shortest path to get to that um, node is three. The shortest path to get to the middle is two, and then the shortest path to get to this node will either be four or no, will either be three plus four, either be seven, two plus three, five, or two plus four, six. So the shortest path to get to the final node would be to start from the source, go to the center, and then go to the last one,
I see.
which should take five. So the answer of this should be five, because within 5 seconds, all the nodes would have received the signal.
Okay. So what's your answer? Or
Answer
like,
is
what's your algorithm?
so the algorithm is we need to find we need to find the we need to find the short let me write this out in the comments.
Sure.
So the algorithm is shortest so starting from the source, find the shortest path find the shortest path to every node in the graph. So starting from the root node in the graph, and and the and once we find the shortest distance from the root node to every other node in the graph, the answer will be the node that is the farthest away from the root. So we have to find the shortest path from the root node to all the other nodes in the graph, and then the answer would be the node that was the farthest.
Okay, how are we gonna do that?
How are we gonna do that? Okay, so we so we should use so since we're doing shortest path, we can use a breadth first search traversal, um, because in breadth first search, whenever we discover a node for the first time, we know that the path that we took to get there was the shortest. So we will use BFS because uh, the path taken the path taken to a specific node from a given
Yeah. Is that true though?
um
Like, what if we come back on the drawing?
yeah,
What
yeah,
if we
yeah,
have
yeah.
like,
I think I so in this case, so that is true if the graph is unweighted. That's true if the graph
yeah,
is unweighted. So I think maybe we can modify the algorithm to take the weighted edges into, because here this is where the edges are weighted.
yeah.
So what I'm thinking is like we just need to tweak the algorithm a bit to take the weight of the edges into account. Because in this case, like if you look at the graph, like the
Okay.
shortest,
How are you thinking of tweaking the algorithm into it?
I think that would be because in BFS, wait, so in BFS, what we can do is hmm, now that I'm thinking, I wonder if no, I'm just thinking like if you could just do a depth first search, or like just do a normal depth first search, and no, wait, I take that back. I think so. The way we append. Oh, so the way we can do this is whenever. Okay, let me draw. Okay, let's go back to the drawing board. I'm at the drawing board,
Yeah.
and we have so in BFS we use a queue. We use a queue. So let's just say we start from the source node, and we start from the source node, and right now we have three neighbors. We have the neighbor at the very right, the neighbor at the very below,
Are
and
you
the
in the whiteboard?
Yeah, yeah. I'm
Okay.
in the whiteboard. You might have to zoom out. You might have to zoom out.
Okay.
Yeah, yeah, yeah.
Okay.
So
Where you at?
in this case, starting, I don't think if you can see if I highlight, so I'll
I
draw it.
see.
So I start from here, right? This source node has three neighbors. This one, and this one. Do you see me mark them?
Yes.
So so the way we can append them on, or push them onto the queue is we can just push by the, so we know that the one on the very, like this one, the one on the very right is the furthest one, so we will push this node on the top, and we can keep track of the distance that it took to get to that node. So we can see to get to that node, like this node, let's just name this node J, node J. We know that to get to J, it took us two, and then we know that the next farthest. So then we have the middle node, and let's name this node Q. We know that the Q is now the one that is the second closest. We know that this time it took to get to Q is 2. Then we know, and let's just name this Z. We know that the time it took to get to Z is 5. And let's, okay. And let's name SJ, and let's name this X. Oops. How do I, wait, I need to delete this. Okay. Hmm. Okay. So we know that the time it took to, so now we have visited, we have like, we have, we have visited S. So now we're done with S. Now we know that the next node is, we now that the next node that we're gonna traverse is J. Let's also keep track of like the min distance that it took. So we know that the time it took to get to S was 0. Now we're gonna traverse J. We know that the minimum time that it took for us to traverse J
Okay.
was,
So what's your data structure here? You're just using a simple queue.
yeah, this is a queue, so this is a queue, and the other is just like some sort of a hash map to like keep track of like the minimum time it took to get to that specific node.
Okay.
Yeah. So we know that we got to J in 2 seconds. So now we're gonna take that off the queue. Now let's just see which neighbors does J have. So J only has one neighbor called X. So we will then push X onto the graph, and we know that it took for us to get to J, it took 2 seconds. So for us to get to X, it will take 2 plus 4, which is 6. So it took us 6 seconds to get to that. So now we're done with J. Now we will explore Q. So till now, we know that to get to Q, the min distance was 2. The minimum distance that it took for us to get to Q was 2. Um, it took 2 seconds. And now let's see, what neighbors does Q have? Q has neighbor J. Q can go to Z, and Q can go to X. So I think here's where we can like look it up. So Q has a neighbor called J, and if we want to get to J from Q, it will take us uh how many seconds? It took us 2 seconds for us to get to Q. And now if we want to go from Q to J, it will take 2 plus 4, 6. So for us to go from Q to J, it will take 6. But if you look in our hash map, we know that we got to J in 2 seconds. So I don't think we should push this onto our queue, because we've already, till now, we've got to J in the shortest path. We have not seen a shorter path yet.
Hmm.
So we will not push J onto the queue. Now let's see Z. And let's, oh, I didn't write this. So let's just say from Q to Z, um, from Q to Z, it takes 1. It it takes one. So if we want to get from to Z from Q, it will take 2 plus 1, 3. It will take us 3 seconds to get to Z, but we haven't seen that yet. So till this point, we haven't gotten to Z. Like even though we did push Z onto the Q when we were at S, we haven't really visited that node yet. So I would still append Z here. So for us to get to Z, it will take 3 seconds, and then for us to get
I
to
see.
X, it will take 2 plus 3, 5. We haven't seen X yet, so let's just add that. So X 5. So now we have visited Q. We can now remove Q from the BFSQ. Now we're visiting Z. So we're at Z, and we know that right now the path that it took for us to get to
Okay,
Z was
let's go down to this last exam. I think I see where you're trying to go, but I'm not sure if it would actually work every time.
yeah, yeah. I can see. The only problem I have is if there's like an infinite loop. The only thing I have
Yeah.
to keep if it keeps infinite looping, that's the only difference. I think you yeah. Sure, sure, sure. Yeah, go ahead. Go ahead.
Okay, how would you solve this case right here? Like, what's the answer for this bottom one?
Bottom one. Okay. So this is 1 1. Wait, this is 1 1. The other one is 5. And what's the from 2 to 1? Is that one?
One, yeah. What's the
And which
answer?
and what's the source node?
This one. Source is here.
So the answer should be oh yeah. In this case, the answer should be 3.
Okay. Let's say these are all bidirectional too.
Oh, these are all bidirectional. These are all bidirectional. It should still be 3. I would think because you go from this node to this node in 1 second.
Yeah. I mean, yeah,
And
it's
then,
three. Okay, run your algorithm on this, and let's just
hmm,
like what I need to make sure is that, like, how do you handle infinite loops, like you mentioned?
infinite loops. I think that one case that in this case. Oh wait, how do I handle infinite loops? Okay,
Yeah.
okay, 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 fine, fine, fine. Okay, let's like draw it out so it's a lot more visibly clear. Let's see, because that's the only concern I have is what if it starts to infinite loop. Um, let's just say it's bi-directional. Um,
Well, let's work through this specific example.
this one, right? The one that you
Yeah, yeah,
drew.
yeah, yeah.
Yeah, I'm just like redrawing it so I could like it's like easier to keep track of
I
it.
see, I see, I see.
Yeah, 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 yeah. So I'm just constructing that. Uh, and so we can go both ways. And this the weight here is 1, the weight here is 1, the weight here is 1, and the weight here is
Five.
right.
Yep.
Okay, and let's name these nodes A, B, C, and D. Let's create our queue here, and let's just also create our like hash map. Do you see it? You might have to zoom out.
Yeah, I see everything.
Okay, okay, sorry. So we're gonna start. So we're gonna start. So A is the source node, right? A is the source node, right? Correct.
Yep.
So A is the source node. So we know that to get to A, we're gonna start at A. So we know that to get to A, it took us 0 seconds. We just started from there.
Yep.
And so now A has two neighbors called B and C. We're gonna we know that the closest one is B because it is 1 second away. Hold up. Let me. I need to put the charger. Hold up.
Charge it up. Charge it up.
Charge it up. It's gonna die. Okay.
Let
Okay.
me fill up my water. Keep talking.
Okay. Okay. Yeah. Yeah. No. So for us to get to B, it's gonna take 1 second. For us to get to C, it's gonna take 5 seconds. So let's just put B onto the queue first. We'll put B, and we know that it takes 1 second to get there. And then we'll put C, it takes us 5 seconds to get there. And now we visited A, and now let's go to B. Now let's go to B. So B can go back to A, right? Because there's an edge back. And so how much time would it? So we're at B. It took us 1 second to get to B, and for us to go back to A, it will then take another second. So it'll be 2 seconds back to A. But
Yep.
if you look in our map, it took us 0 seconds. So we've already discovered a shorter path.
Sure.
So I don't think that we need to push that onto the queue because we
Mm-hmm.
already saw A before. So it doesn't make sense.
Sure.
So now from B, we can go to C, and that's this other neighbor. And to get to C, it will take whatever time it took for us to get to B, and the time it will get for us to get to C, which will be 1 + 1, 2. We haven't seen two. We haven't seen C yet. We haven't seen C yet, so we'll just like add that to our queue because we haven't seen it. So now, um, we have visited B. So let's just store it in our map, and let's take it from our queue. Now we're at C, and now we're discovering the path. Now we're discovering the longer path. So from A to C, which we know was 5. C can go to B, and from C, okay, so from C we can go to B, from C we can go to A, and from C we can go to D. So first, let's check the case where we go from C back to A. And just want to make sure that in this case the weight is also 5, right? Like both directions, it's 5,
Yep.
correct?
Yep.
Okay, in this case, the time for us to get to C, if we look at the top of our queue, was 5 seconds. For us to go back to A, it's going to take another 5 seconds.
Mm-hmm.
So that'll be 10 seconds to get back to A. But if you look at our map, we discovered a shorter path.
I
Like
see.
we know there's a shorter path, so we don't need to append that. Because like it doesn't make sense. We already visited A using a shorter path. Now, if we want to go from C to B, it will take us 5 plus 1, 6.
Yeah.
But we saw a shorter path, so I don't think we should append that. Now, for us to get from C to D, we haven't seen D yet. It's not our, so let's add it. So for us to get to C to D, it should be 5 plus 1, which is 6. So let's add that. So D to so from it will take. So now we have we have visited C, and we've seen that it took us 5. And now we can pop it off from the stack. And now we're gonna visit C again, but from the path coming from E. And I think here's where we can tweak the algorithm because now we're revisiting C, but we took a shorter path because before we took a longer path. So maybe we should like maybe we can here's where we can tweak the algorithm and just do the same math again. Like now we know that we got to see it from a shorter path, so let's prove that we do the same again. We can go back to A. Uh, we can go back to A from 2 plus 5, 7.
Okay.
So if you're going to go back to A from C, it'll take us 7 seconds, but we got to
I
A
see.
quickly, so we don't
Okay.
need to do that. If we want to now go from C to B, it will take us 2 plus 1, 3 seconds to go back to B, but it took us 1, so we should not go back. For us now to go from C to D, it will take 2 plus 1, 3. We don't have D stored, so let's just put 3. And let's mark that that took us
Yeah.
2 seconds to get to C.
Okay. That stopped you there now because we're
Yeah,
45
but
minutes in. I think, yeah, you're kind of getting there, but I don't know for sure if your solution would actually work. Like the. You can hear me,
like
right?
I'm trying to think. Like, is this a lead code? Like, I've never done this, but I'll try
Have
it.
you done a Dijkstra's algorithm before? That'd be the optimal then.
No, so I never did Dijkstra's algorithm, like because I think most of these graph problems are usually unweighted. That you see in these
Yeah.
interviews, and so like you can like replace that with BFS. So I
Yeah,
just like
exactly. But since it's
yeah,
weighted, you have to do like a
yeah.
Dijkstra's or something.
Oh, I understand. Yeah, I know. I've never had to use Dijkstra's. So
Okay.
I see. I get your point. Yeah. So okay. Yeah. I'll probably tweak. This is a good one.
It's a
Like
good one, right? Yeah.
it got my brain to work. It could work. I do not know. Like I have a feeling it worked, but like the only way to
It
know is
might
just
be
like
try it and then send it. I think it just might be inefficient because I think
yeah. No, it might be inefficient. You're correct. You're correct.
because pretend I get to this one, I already seen it, and maybe yeah, I don't even know. It might be inefficient. I think we'll just need
It
to
might be inefficient. I think it will work, but it might be inefficient. I could get TLE.
yeah
Like that's it. Yeah. But no, this is a good one. This is fun, dude.
yeah.
Thanks.
All right, Shabaj, nice to see you. We should do some more
Yeah.
collabs, work on
So
some projects.
we should do it like in person or something. I
Yeah,
don't
I'm
know. All
down,
right,
bro.
cool.
All right,
All right,
catch you on the next one.
all right. Thanks for the
All right,
stream, dude.
peace.
Bye.